All right. The recorder is doing its recording, and I will proceed. So, as I did in the first unit, I'm breaking this unit into two parts. Not three parts, just two parts. And the first part that we did were quantities and chemical formulas. So those guys over there working away on their tests, they're looking at the chemical formulas, how to get masses, all that good stuff. And so that was an introduction on how to deal with just chemical formulas. Now we want to move on and apply this to chemical reactions. This is the purpose of chemistry. We're finally at the part of the year, the part of the course, which is really why we do chemistry. A little bit of history. So in like the late 1600s, I'm not talking about Lavoisier now. Lavoisier was the late 1700s, so about 100 years before. Sir Isaac Newton, he was the other guy that was on the wall that got painted over. Sir Isaac Newton had quantified physics. And if you've taken physics, we need to put phones in bags. Phones in bags. No, you're not. You're going to put it away. I don't care. Put it in your bag. Okay, so Sir Isaac Newton took stated the laws of motion. And if you've taken physics, you know what I'm talking about. First law, second law, third law, good stuff. And was able to quantify physics. Before that, it really didn't have numbers. People had an idea of the way things moved. They didn't really calculate it. And by quantifying physics, that really kind of was a game changer, because physicists could now take an object that was moving, like the moon or even just a ball or a cart, and could do some math and predict where it would be in the future. It became predictive, which was really awesome for things like engineers, building things, understanding the way it worked. It took another 100 years for chemistry to kind of catch up. The reason it took 100 years had to do with scale technology, how to weigh things. And scientists, many of them, chemists, didn't think you had to weigh things. You just had to kind of know how to mix it together. And not worry too much about how much of the product you would get. But Lavoisier, and I don't have my Lavoisier book, but Lavoisier, he was able to quantify things by measuring everything. And that then brought us to be able to use chemistry predictively. If you had so many grams of reactant A reacting with so many grams of reactant B, you could predict how much product you're going to get. And that again made it predictive. And that's powerful. If you can do a calculation and say, when we do this chemistry, we're going to get this, then that's pretty good. You can predict what's going to happen. So that's what I'm showing you today. I'm showing you the basics on how we use chemical reactions to predict either how much we need to make a reaction go or how many products that we're going to get. All right. A couple of definitions. You're going to take the earbud out of your ear as well, please. So quantitative analysis, we've already started in on that. We did that with our last lab, where we did a bunch of measuring of masses, and you had to do a quantitative error analysis. You had to explain things numerically. It's just simply the measuring of quantities. And the next term there is stoichiometry. It's a great word. It's got three parts to it. Stoi, from stoichion, theo means chemistry, and metry means measurement, okay? So the first part, the stoichion, really means just mass or weight measurement. It's a Greek, I believe, portion of a word. So this literally means chemistry, weight, measurements, all right? And it's the term that we use whenever we deal with an overall balanced chemical equation to figure out relationships between reactants and products. So this is all about figuring out various quantities in a balanced chemical equation. All right, so let's talk a little bit about what is in a balanced chemical equation so that we can make some sense out of the calculations that we're going to do. Thank you. If I were you, I would just kind of start here, leave maybe about a half a page. There's just a couple of definitions at the top that you've missed. All right. So let's talk a little bit about the parts of a balanced chemical equation. We've already done balancing. So let's take a look at what this all means. Again, we know that each of the chemicals represents the entities that's in that particular thing. We've got some hydrogen molecules, some oxygen molecules, and some water molecules. So looking at the coefficients, again, we sometimes call it the stoichiometric coefficients. I haven't been using that term yet, but now I can. Looking at the coefficients, that tells us the ratio of the amounts either required, I need 2 parts hydrogen to 1 part oxygen, or the reactants to products, for every 2 hydrogens, I'm going to get 2 waters. So they represent almost like a recipe for making chemicals, just like if you were to bake some cookies. If you've got the cookie recipe, it'll say so many cups of flour and so much sugar and so many chocolate chips, and it's essentially a recipe. And so these coefficients really tell you how many of those things are needed to make it. So here we need, say, 2, oops, oh, I didn't orient the board, which is going to make it really hard to make a movie, which means I've got to stop for a moment. Very embarrassing in the middle of a movie, but I'm not stopping. Orient. Oh, you didn't give me that last one. Let's see what it looks like. 2 molecules. That's not bad. For every 1 molecule. That looks good. That's going to produce 2 molecules of water, right? So the ratio tells us how the molecules come together. Now, again, like I said, that's like a recipe for making cookies. But if you've got like a large number of cookies to make, let's say you're having a cookie party, it could be a thing where everyone comes with cookies, and you have to make a large amount of cookies, then you're not going to just use 2 cups and 1 cup, but you might double the recipe or you might triple the recipe. Same thing in chemistry, especially if we're talking about molecules. Molecules are way too small. So we always talk about moles, large groups. So this also could represent the fact that if I had 2 moles of hydrogen, I would need 1 mole of oxygen, and that would produce 2 moles of water. That's a much more convenient thing, because if I'm going to work with moles, all right, then I can easily convert that to mass. I know how to do that. I can use a molar mass, and I can make a conversion. Okay? So moles is far more convenient. All right. The mole ratio, then, is a very important ratio so that we can find information that we need. Now, in the past, I would have written the mole ratios as conversion factors. But we're getting away from those conversion factors. I think next time I teach it, I won't even mention conversion factors, because we can do everything with formulas, and we can do everything with ratios. And that's why I'm making a new video, because the people who are writing tests are going to have to watch a video tonight in order to get caught up. And my old video talks about conversion factors. And really, this is the way I used to teach it, and this is the way that I learned it. So it's not a bad way. It works just fine. Conversion factors are convenient. You can put a bunch in a row, but sometimes it's better to think of 3 distinct calculations. What am I doing here? What am I solving for here? What am I solving for there? So there's many ways in which we can write ratios. In this case, to just point out some mole ratios, I'm going to just use the ones with the 2 dots, right, with the colon, how you usually write it in math. So if I wanted to write a possible mole ratio to represent the ratio between hydrogen to oxygen, right, if I know how much hydrogen and I have to figure out how much oxygen is needed, I would say it would be a 2-to-1 ratio, H2 to O2, right? So if I have 2 moles of hydrogen, I only need 1 mole of oxygen, because it's a 2-to-1 ratio. And I can compare hydrogen to oxygen. What if I have a question where I've got so much hydrogen and I want to figure out how much oxygen do I need? That would be like if you knew you had like 5 cups of flour left, how much sugar would you need in order to make your cookies? That's a valid calculation. We can compare any 2 things with a mole ratio. I could go 2 to 2 would be H2 to H2O, a 2 to 2 ratio, or essentially a 1 to 1 ratio. For every 2 moles of H2 we have, we're going to make 2 moles of water. You end up with the same amount. I can make a mole ratio out of any combination. There's only one left, I think. I think the O to H2O. I guess if I wrote that at the top, the O2 to H2O, what would the ratio be of O2 to H2O? That would be a 1 to 2 ratio. A 1 to 2 ratio. So for every 1 mole of O2, I'm going to get 2 moles of water. And it's just about ratios. It makes it pretty straightforward. So the next thing I'm going to do is I'm going to show you how to do a problem and how we set it up in a specific way. All right. And I have to orient the screen one more time, and I'll do it. The right side is a little goofy. I'm not hitting the right spot. And it's very important that I get my writing in exactly the right spot. And I'll explain why in a minute. So I'll let you write that question down, and then I'll orient the board one more time. So in the examples that I'm going to show you today, we're going to start with moles of one reactant and calculate the moles of the other reactant or product. They're the simplest of all of our stoichiometry problems, from moles to moles. Tomorrow, we're going to start with a mass, but that's okay. We know how to turn mass into moles with a molar mass. And so adding on to it shouldn't be very difficult. It's using stuff that we already know. Now, just like I attempted to indoctrinate you, like math does, in using the molar mass. How do I convert grams to moles? Molar mass. I want to indoctrinate you here in this situation as well. If you've got a question that involves a chemical reaction, and you've got to kind of think about the words, calculate the number of moles of SO3 produced when an excess of SO2 is reacted with 2.35 moles of O2. The terms reacted with, produced. Whenever you have a stoichiometry problem that involves a chemical reaction, the first thing you need is the balanced chemical equation. Dana is writing with her eyes closed. That is amazing. That is amazing. I just recorded that. I'm going to put this on the internet for everyone to hear. But that was amazing. You literally kept writing a little bit with your eyes closed. That's incredible. I'd like to see what your notes look like. So I'm going to orient the board, but I need you to do a balanced chemical equation. And as I'm orienting the board, go ahead. All right, start with a balanced chemical equation. You can see where it says is reacted with, so we've got reactant, and is produced, so we've got the product. So go ahead and do that as I orient this board one more time so I can write on the far side of the screen. All right, that's better. So what do we got? What are our reactants? Okay, so I've got SO2 plus O2. Yep. SO3, SO3, and now I need to balance it. So what am I going to have there? What am I going to put for coefficients to balance it? Yep. I could use a 0.5 in front of the O2, you're right. But because I'm showing you the way mole ratios work for the first time, I don't want a decimal in it. You see what I'm saying? We can use a decimal, but I don't want it to be in my very first example. So how do we fix it? What do we got? You're wanting to do a 3-2, but that isn't going to help me here. So that's not going to help me in this case. So that's not going to work. Yep. A 2 and then a 2? Yeah, because I would have had a 0.5 here, and if I double everything, it takes care of it. 2 and 2. Now, having said that, when I give you guys your test, it'll be next week sometime, and it's got a whole bunch of stoichiometry on it, and you can't get a balanced chemical equation, it's impossible to proceed. You can't do the rest of the question because it all starts with this. And a question like this sometimes might be worth something like 5 or 6 or 7, where the first 3 marks are the balanced chemical equation. Now, if a feeling of panic is going through, I do have a little bit of a solution. What I do with a test like this is if you can't get the balanced chemical equation to begin with, you can put up your hand and say, I don't know what it is. I'll give you the balanced chemical equation, but you will forfeit the 3 marks that are part of getting the balanced chemical equation. But at least you'll be able to continue on and finish the math. So that's the way I kind of deal with that. Okay. So how do we deal with a question like this? Do it very systematically. The way I'm going to write these things and the position that I'm going to write them are super important. So I want you to write them just like exactly where I tell you to put them. The first thing I want you to do is I want you to imagine that there are 3 lines underneath your balanced chemical equation. And because you all use lined paper, you don't have to imagine it. There are 3 lines underneath your balanced chemical equation. No, the space is what I'm speaking of. Now, in the first line, in this area, is where you will put things like grams. But in my question right now and in the questions I'm going to teach you today, there are no grams. There will be tomorrow. Other things that can go in this one here is entities. Sometimes I give you a question where you have entities or trying to find entities. They'll go in that row. In our next unit, we're going to learn about chemistry that takes place in solution, dissolved in liquids. In that case, we'll be measuring with things like milliliters and liters. That'll also go in that row. In the second row is where we put our conversion number, the number that we put in the equation in order to figure out moles. So if it's grams, I'll put a molar mass in there. Yeah, if it's entities, I'll use Avogadro's number, Na. And if it's milliliters, we will use a concentration unit called molarity, but I'm not even going to put it in there right now because it has no meaning to you. But we'll have another unit in there to solve it. And down in the bottom is where we put moles. All right, so that's the mole line. And so the calculations we're going to do today, and I'm only going to do 2 examples, and I'm going to let you work on a sheet. We will only be using this bottom line. And this morning when I went around and helped people, many people just forgot about the lines and just wrote stuff anywhere. The reason I write it in this way is to set the problem up in steps so that you can solve it. So, calculate the number of moles of SO3. So directly under the SO3, in the mole line, because it says moles, I will put question mark, moles. That's what we're looking for. Is produced when an excess of SO2, so lots of SO2, I don't have to worry about it, is reacted with 2.35 moles of O2. Under the O2, 2.35 moles. So its position is important. We will learn in tomorrow's lesson that I can move up and down from the gram line to the mole line using the molar mass, using the equation for the molar mass. We're not doing that today. In the mole line, you can only move horizontally, so I'm going to go from here to here, like my little map that I made before. And to go from moles of one thing to another, I use the mole ratio. And as I showed you in the last slide, the mole ratio comes from the coefficient in the balanced chemical equation, the stoichiometric coefficient. Now, I'm going to write the ratio instead of as the dot notation as a couple of fractions, and let me show you where it comes from. So what I will write in this case is 2.35 moles is represented by the coefficient of 1, where x moles, the question mark, is represented by the coefficient of 2. So there is my 1:2 ratio in fractions, so I can cross multiply and solve for x. You might already see that if this is doubled on the bottom, then this has got to be doubled on the top in order for it to be equal. That's all that really means. For this to be equal to this, if the bottom number is doubled, then my top number has to be doubled. That's the ratio. How do you do it mathematically? Mathematically, because you've got a 2 on the bottom, you could multiply by 2 and multiply by 2. I'm bringing the 2 up to the other side. Okay? By multiplying by 2, I have x by itself at this point, and x equals, well, what's 2 times 2.35? 4.70. 4.70. Which means my question mark is 4.70 because there's twice as many. Therefore, we can say there is 4.70 moles of SO3. Okay? Some very important things. I've used up all my colors. I'm going to use blue again. We don't write in the 1, but that 1 went over there. And I don't need to see all these steps. This is the first time running. The only thing I would write here is what I'm writing in white. And that 2 went over there. Okay? Let's do one more example, and then I will let you work on practicing this. Okay, next example, right there. It's okay, I'll get it. Oh goodness, there's blood on the floor. Must have been down there a while. I'll put a paper towel on there so we don't step on it. Again, when you're done writing, try to write a balanced chemical equation. The evil part of this one is that I've not given you the formula for phosphoric acid, so you have to think about that. And I haven't given you the products, so you'll have to think about that. What's that? Did I? Yes. No, I didn't. I gave you one product, but there's other products. Phosphoric acid. Yep. So it comes from phosphate, right? We need all the H's. H3, CO4. I tell you that water is one of the products. What is the other product? Yep. Balance it. Na with a 3 because we're crossing over. And what do I need to balance that? The balancing is really, well, it's all important because if you don't have the formula right, you can't balance it, right? What do you got?
You need 3 for the NH. The NaOH, sorry.
I need the 3 there.
And then you need a 3 in front of the H2O and a 2 in front of the...
I need a 3 here.
Yeah.
And what are you adding?
A 2 to the H3.
Yep. No, because I've got H's in there.
Oh.
That's it there. That's balanced there. All right. So, again, with these first ones, if you don't write the 3 lines or leave the 3 lines, it's not as much of a big deal, but because I said determine the number of moles of water, question mark moles. Yep. Double displacement reaction. Okay. 0.76 moles of phosphoric acid. 0.76 moles. I can go across the mole line with the mole ratio. So I will set up a ratio between the phosphoric acid and the water. I'm not interested in the sodium hydroxide at this point. Could ask that question, how many moles of sodium hydroxide is needed, but that's not what we're asking. 0.76 over what? Equals X over what? What am I putting where, Angel? 0.76. Yep. X over 3 from the coefficients. All right? I'm bringing the 3 to the other side, and I'm done. I've got it. X equals 3 times 0.76 divided by 1. X equals. There are examples that you will encounter that don't have a 1 there because it's got like a 2 or a 3. Then you'll just divide as well. 3 times divided by 1. You don't have to divide by 1, it doesn't do anything, but if there was a coefficient of 2, then you'd have to divide by 2 because it would be a 2 to 3 ratio. What do we get there for 3 times that number? What do we get? What do you got, Angel? 2.28 moles. And then I can finish the question. Therefore, 2.28 moles of water is produced. Okay? Yep.
The 3 that you put under the X from the water.
Yes, correct. So these numbers here that are on the bottom are the coefficients of the 2 things that I'm studying. The unknown becomes the X, and the 3 goes underneath. That number becomes the top, and the 1 goes underneath. And that tells me what that unknown number is. Okay? All right. There is a worksheet on Google Classroom. Part A, all the questions deal with just the mole ratio. You might get that done. There's only something like 7 questions. If you do, you might want to try the ones that have masses in it. It's not a big deal. I could have asked here, how many grams of water is formed? Well, we already know that if I know the moles and I want to get grams, what do I use to convert moles to grams? So I would then have the molar mass of my water in there. I would do my calculation and I could get the grams. That's what we'll do tomorrow. We'll add on a few other steps. So if you get done all of those, you could probably try the first 3 of the next section too. They're not too far off. you can work? The answer is, oh, that last one I didn't have my microphone on, so my voice will be in and out. That's okay. You can work away, all right?